Recorded is rolling. It is Friday, January 24th. You guys remember yesterday you were doing this pendulum lab, trying to figure out if I got this pendulum rigged up. Like what equation is governing the motion of this pendulum? Like what laws of the universe? Right. So we're headed towards this. This circle time period equals something. Right? And you guys were testing out three independent variables. Right. Okay, so here, guys, everybody focus here. So changing out the masses, changing out the length, changing out this angle, which was three different experiments. That's why I set you guys up three different tables here. Okay. And then we're headed towards these graphs. I'll help you guys put together the graphs today, and we're working towards this conclusion. Actually, we're going to find a proportionality, but it should match the textbook version of the time period. Right. Of course, we'll find the proportion version. All right, so graphs, conclusion, and then you guys, AP, I had you guys do a write-up. Here, show you guys this from yesterday. Specifically for the experiment where the length was the independent variable. So we were changing out the length, so just focus on that one. All right, we'll score the write-up. I have the scoring key ready to go right here. So we do that too. All right, before we dive into that, some other things. You guys remember, I showed you guys this a couple days back. There's this STEM Career Showcase. This is next week on Thursday. I did scan this and uploaded this to Google Classroom so you guys can get a better look at that. Right, so that's on Google Classroom as of this morning. All right. Yesterday, I gave you guys the spring thumbnail notes. Sorry, here. So if you didn't get a chance to get it, these are for you guys. You guys are supposed to take these. All right, so if you didn't, then got some extra ones out there. You guys can pick up a pack of those. So it's for you guys. And then you guys AP, you guys also have these chapter 13 puzzles. I would like to get those into your hands so that if you want to read them ahead of time or start working on them, right, you can, because we're going into the weekend. Right, so circle the recommended ones. I also open up the next AP classroom. Right, so this all related to harmonic motion is what this is. Right, harmonic motion. All right, so here we go. All right, you guys ready to put some graphs together? Some graphs. All right. So, to finish off this table here, you guys know there was, here's kind of what I would recommend. Here's how I would adjust myself. I would then time for 10 oscillations in some number of seconds. And then suppose that came out to like, I don't know, 9 seconds. Then I could find the time for one oscillation, which is the time period. That'd be 0.9 seconds, right? You just divide by the number of oscillations. In my case, 10, if I did 10. Okay. You could have done 5, that's okay. I did 5 oscillations divided by 5. You guys remember, guys, what's the purpose of doing multiple oscillations and dividing by the number of oscillations? Why is that better?
Reduce error.
Yeah, reduce error, right? Because your error starting, stopping the stopwatch also gets divided by that number, which just makes it more accurate. Okay? And then actually, there's a reason there's still more columns too, right? If you, some students I saw yesterday put gravity field, which is true, that could actually be a variable, but we're kind of locked into the gravity field, so can't really test for that. And then but there's still another column that could be, but we'll run into that later. All right, so let's try this first. Let's knock out, thank you, M and theta, or the masses and time period, and theta and time period, and we'll hit length and time period last because that's the write-up that I would guys do. So that'll be nice. All right, so mass and time period. Who wants to volunteer some data for mass and time period? Mass and time period. All right, how about Alec? You got some good data for that? All right, so let's do graphs here. Now, you guys got space for each of these graphs. I'm gonna put on a big old page just to, so it'll definitely look better for the dot cam and the camera. All right, so let's do mass on the horizontal because I'll treat it sort of as an independent variable, so I'm gonna think about that. Okay. Now, if you went the other way, if you swap the axes, that's okay. You still get the correct conclusion out of this. I'll put time period up here. It's gonna be in seconds. Okay. All right, so Alec, what's the largest mass you guys used? 500 grams? Right. Actually, you know what? I'll change this to grams. Right. That'd be right. 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 So that up to 500. So I want to scale this up to 500. See, how can I do that? How about I go? How about every 2.5 centimeters? So 1, 2, 3, 4. Okay. So you guys know in this class, your graphs are always going to start at 0. In the real world, look for graphs that don't start at 0 because sometimes there's some deceptive graphs out there, but in this class, they're always going to start at 0. So I'm counting in grams in this case. Okay. Oh, guys, a common question that had come up yesterday is how do you convert from grams to kilograms? You divide by 1,000, right? Which is 3 decimal places. So if you want to do that, you can do that. It's perfectly fine. Okay. And Alec, what was your longest time period for this?
For
Huh?
the longest was 1.723.
1.7 seconds. Okay, so let's round up to about 2 seconds. So maybe we'll go 0, 1, 2. So 0, 1, 2. There you go. So graph starts at 0, 0. Yeah. Okay. All right. Close 1.5 here, close 0.5 here. All right, that should contain all the data right there. Okay. Yesterday, before you guys started collecting data, I had you guys hypothesize. So as you go from small masses to large masses, right, as you increase the mass, would that increase the time period, decrease the time period, or have no effect on time period? So you guys did some hypothesis, right? But we're about to find the answer, and maybe some of you guys know the answer already. You guys got the data. All right, so what's one coordinate on this graph?
50 grams and then 1.644 seconds.
All right, 50, 1.644. It's right about there. All right, so I'll do coordinate 50, comma 1.64. All right, so this is grams and this is seconds. All right, what's the next coordinate?
300 and 1.624.
You say 300 and
100.
100 and what?
1.624.
1.624. 1.624. It's right about there. All right, so 100, 1.627. Okay, so this is grams and seconds. All right, next one.
200, 1.714.
200, 1.7 something, 5. Ooh. Ooh, actually, you know what? Now I'm looking at my points are off a little bit. That's all right. Yeah, shift them up a little bit. All right. So 200, and you said 1.7 something?
Yeah.
Okay. So grams, seconds. All right. Next one.
500 and then 1.722.
1.722. All right. Got 500, 1.72. All right. So, okay.
Final one is 20 grams of 1.637.
All right. 20 grams and 1.637. All right. So get there. So 21.63, 637. Okay. All right. So this is seconds, grams. All right. So what's the relationship, do you guys think? Yeah, no relationship, constant, right? Constant, no relationship. Right. Right. So should I connect dot to dot to dot, or should I throw down my roller and clean sweep? Yeah, about the second thing I said, right? Go like that. Okay. Right. Now, this graph, yeah, because I've seen this, year over year. Usually this graph does slope up a tiny bit, and I think this one does too. So it's actually kind of predicting it would. So maybe it's not exactly constant. And why do you guys think it might curve up just a tiny bit? Yeah, the string length changes. Yeah. Guys, if you hang this mass on the string and you unhook it and hang on this one, okay. So you suppose they're like the top of the string might go to here and then to here. Do you guys see the effective length of the pendulum? Guys, the effective length of the pendulum, did you measure from the pivot point down to the center mass of the lab weight? Okay. And if you did, the larger lab weights are physically larger, and so the physical length of the string is actually a little bit longer. So we're actually getting a little bit of a length effect, and that's why this graph's not perfectly flat. It goes up a little bit, okay? Because length is a little bit variable here. All right, but basically no relationship. So when we're headed towards this master equation right here, time period equals, guys, does the mass of the bob even show up at all in this equation? No, it's not even going to show up. It's not even a factor. Okay? And you know what? You may have hypothesized that ahead of time, because you know what this is actually kind of related to is the Galileo question going back to 1589. You guys remember Galileo dropping balls off Leaning Tower? Small stuff, big stuff, didn't it all fall together and land at the same time? Right? So they were, from a physics one perspective, there's two competing effects. Larger stuff is more weight, but it's also more inertia, and the two effects cancel out. Right? Okay. So if you just put that on pendulum, yeah, the mass or weight also cancels out. Okay. Yeah, so that's what we're seeing right there. All right, so that is mass is not going to be a factor in the pendulum equation. All right, we got next. We got Yeah, angle. All right, who's got some angle data to volunteer? Angle data. All right, let's go. Joseph. Okay. So we have to up some actors again. You guys got some actors in front of you already. Okay. So we're doing time period and seconds as a function of angle and degree. Oh, you know what could have made this better? Maybe we should put a title on here. T versus theta. We should have done the last one too. Slap on a title real fast. Okay. So yeah, the last one was T versus M. Okay. This one's going to be T versus theta. Okay. All right. So Joseph, what was your largest angle used?
Our largest angle use was 50.
50 degrees? All right. So I'm going to scale that. Let's go 10, 20, 30, 40, 50. So 0, 10, 20, 30, 40, 50. Okay. Of course, you guys, this graphs are starting at 0 and then scaling up from there. All right. What was the longest time period?
The longest time period was 7.88 seconds. It's 1.7.
Huh? What, 1.7?
1.788 seconds.
Okay. So go 0, 1, 2. So 0, 1, 2. All right. Let's get some coordinates here. What's one coordinate?
So one coordinate we had was a angle of 20 degrees and a average time of 1.723.
All right. 20, 1.723. All right. Sorry about that. So 20 degrees, 1.723 seconds. Okay. Next one.
The next one was a degree of 30 and a we got a time of 1.751.
1.75. Okay.
That's one.
So that should be right there. Yeah. Okay. So at
Sorry.
30 degrees, 1.751 seconds. Okay. Next one.
The next one was a time of 1.764. Rounding that up, oh, it's gonna be 1.765. Sorry,
Okay.
1.
How many degrees?
Degrees of 40.
40. Okay. So 40 degrees, 1.76. 40 degrees, 1.76 seconds. 40 degrees, 1.76 seconds. All right. Okay, next one.
And the next one is going to be a degree of 50 and a average time of 1.785.
All right. So angle 50 degrees, time 1.78 seconds. All right. So 50 degrees, 1.78 seconds. All right. Do you have a fifth point? Or just this far?
Yeah.
Okay. All right. Okay. So what trend line do you guys think? Yeah, is this also probably pretty constant? You guys think? Okay. It looks like it maybe slopes up a tiny bit, but it's pretty much constant, isn't it? Right, you guys get it? Pretty much constant. Okay. So do you guys think that the angle theta is going to show up in this equation at the end? Yeah, also not going to show up at all. Right, it's also independent. Okay.
Wouldn't it have to be logarithmic because it has to start at 0? Because if I have 0 degrees, then it's not gonna have any time.
Well, not necessarily. Maybe like what if you pull it to like a tenth of a degree and let it go back like a tenth of a degree, so you get a point like really close here. It might be like this point right here, maybe something like. Okay. So yeah, so it'll still take the same amount of time to oscillate back and forth. It just might like be barely visible. Yeah, but it's still the same time. Yeah. Okay. So yeah, this is about this. Was okay, so the angle theta is not not going to show up in the equation. Oh, I remember what I was saying. So if AP asks you some question really about this on say a free response question, I've seen this in the past. One of the details they're looking for full credit is you mentioned a small angle. I'm going to write that down. So usually they keep it like less than 20 degrees. So I'm going to do this right here and say small angle, right? Because when you get the angle too big, this formula doesn't that we're headed towards maybe doesn't describe it exactly, right? So maybe that's why these points don't lie exactly on a constant line, it slopes up a little bit. Okay. So really what AP considers is really just this part of the graph right here, which is going to be pretty well constant. Okay. Okay. All right, so we got to chase down one last relationship. Okay. And so he's got data for time versus length. Time versus length. Okay. All right, Asher. Okay. So we got some axes going. We're on time period versus length. Okay. Time period in seconds. Like, Asher, what was your longest length? 69 centimeters. So we'll do length in centimeters. Okay. So scale this up to, let's see, 10, 20, 30, 40, 50, 60, 70. Yep, that'll do it right there. So 0, 10, 20, 30, 40, 50, 60, 70. All right, and what was your longest time period? 1.7 something? Sorry, okay. All right, so let's go 0, 1, 2. So 0, 1, 2. They're on 0.5 and 1.5. Okay. All right, let's get some coordinates. What's one coordinate? Yeah, of course, right? 69 centimeters, 1.74 seconds. 1.74 is right there, there. It's right about there. Right. So 69 centimeters, 1.74 seconds. All right, what's the next one? 56, 1.52. 56, 1.52. 56, 1.52. All right, so this is centimeters and seconds. All right, next coordinate.
45, 1.41.
45, 1.41. Forty-five, 1.41 centimeters seconds. All right, next one.
31, 1.19.
31, 1.19. Centimeters seconds. All right, next one.
18, 0.93.
18, 0.93.
That's all.
Yeah, all right. That'll do it. 18, 0.93 centimeters seconds. Yeah, that's pretty well what I'm looking for right there. Okay. What relationship do you guys think? Square root? Square root, you guys think?
Yeah, no, that's it.
Yeah. All right. You guys see lots of parabolas and square root graphs in this class from labs, and at a glance, it's like, oh, that looks kind of linear. But then if you think about it, it's like, oh, I don't know if that quite works. Okay. Because I did see, yeah, this data looks like it does curve a little bit. Okay. And if you thought it was a straight line, oh, well, here's kind of labs we've run into in the past. Like, okay, well, this would have a huge y-intercept. And what would that mean? That would mean as the length approaches 0, the time period is approaching some definite number. It's like, I don't know if that quite makes sense. Right? Now, if you wanted to do the scientific version of this, you could pull up new pendulums and just make them really, really short. Like try a 5 centimeter long pendulum and see where's that land. And I bet it lands somewhere kind of down here. Right? I bet we're looking at, kind of dash this off because here's what I'm imagining. I bet it's going to approach 0, 0. Right? And it's, yeah, some kind of square root looking curve, right? At least that's my suspicion. I'm suspecting a square root. And you guys have seen this lots of times before because this has shown up over and over in past labs. Is if you suspect either a parabola or because the square root is just a sideways parabola, right? Turn the parabola sideways, it's a square root graph. Right? We can check that by doing a linearization process. So this is what's going to lead to the 4th set of axes. That's why I have 4 sets of axes lined up for you guys. Right? Because we've got one more to go. Right? So we're going to do a linearization graph. And there's 2 different ways to linearize it. What's one way that it can linearize this graph if I suspect a square root? Square the time. Yeah, great. So here in the margin, I'm going to maybe how about on gold ink? I think this will show up. Okay. I suspect time period is proportional to the square root of L. that show up on the screen? Kind of. Okay. Alright, so if I graph t versus the square root of L, should that line up in a straight line? That's the other way I could do it. Okay. But I want to try it this way. I want to do t squared proportional to L, right? Because that would also be true. Like if one's true, the other is also true. Right? Notice I'm saying proportional. Think of that kind of like an equal sign, but maybe I'm leaving off like the gravity field and some other things. Right? So that's what I'm going to graph. I'm going to do time period squared versus the length. So let's put time period squared here. All right, now we're in abstract land because it's got square seconds. I'll do length and, well, meters or centimeters. Right. I'm really looking for a proportional relationship. So whether you do meters or centimeters or inches for that matter, it should line up in a straight line. It goes through the origin. Let's see if that's true. Okay. So I'll keep exactly the same length as before. So I'll scale this up to 70 centimeters. Let's go say 10, 20, 30, 40, 50, 60, 70. So 0, 10, 20, 30, 40, 50, 60, 70. Okay. Now all those time periods, calculator time. Well, the longest time period was 1.74 seconds. If I square that, I'm getting a little bit over 3 seconds, 3.0 something. So time squared, let's go 0, 1, 2, 3. Okay, and then the point is going to just be a little bit above that. So 0, 1, 2, 3. Points a little bit above that. All right, so all the data points will fit on the space. All right, so first point at 69 centimeters, we'll call it 3.03 square seconds. So 69, 3.03, which is right about there. So centimeters, square seconds. All right, next one. Take 1.52 seconds and I square that. Oh, I should have said first. Let me dig through this a little bit. Right. Under data table, one of the columns was actually for this. Is if this was a pre-response question, like exactly this experiment, they might be looking for this. An AP grader would be looking at your table. If they see t squared in the unit square seconds, then that would be a clear indication to them that you know what you're doing. Right? Of course, by the time you take the AP exam, you will know all these formulas. Right? You guys, of course, have access to these formulas here. I guess the answer, you guys, you see the answer is like right here, right? Right. So it's been there the whole time. Haha. And also on those thumbnails I gave you guys yesterday. Okay. And if they see this on your lab table, because they might give you like a blank lab table or some variables and leave everything else blank so that you can write in your own columns. Okay. If they see that, it's like, oh, yep, the student knows what they're doing. Okay. So 1.52 squared, that's 2.31. 2.31. So 56, 2.31. Right about there. So 56, 2.31. So this is centimeters, square seconds. Right. 45, 1.41. 1.41 squared is, of course, almost 2, about 1.99. Right. 45 and 45, 1.99 centimeters square seconds. 1.19 squared. All right, 1.42. So 31, 1.42.
I'm sorry, sir.
So centimeters square seconds.
I'm sorry, sir. I'm sorry.
Then let's see, 0.93 squared, it's like 0.86. So 18 and 0.86, right about there. 0.86 centimeters square seconds. Okay. Yeah, guys, do those points pretty well lie in a straight line? Yeah, a lot more obviously than what I was calling probably a square root curve. Yeah, and it okay. Actually, it looks like it's got a little bit of a negative y-intercept. I don't know. I don't know why, but it's pretty close to the origin, right? Pretty close to the origin. And ideally, it would go through the origin. Okay, there. Good. They round that a little bit. Say it pretty well goes through the origin. All right. Okay. Now, if that's true, then uh, then my suspicion here, time period squared is proportional to L is true. Okay. So when we're going to make this equation, T equals something. Like if you want to make the full equation, well, T equals, I guess if I square root both sides, be something to do with square root of L, and maybe there'd be like a constant in front. Hey, we can get the slope of this line, right? Call it like y equals mx. Let's pick 2 points on the line and do rise over run. Or yes, thank you. So we pick 2 points on the line, I do a rise over run here. So 2.31 minus 0.86, there's the rise in square seconds, divided by, and then in parentheses, I'm going to change this to meters. Is that okay? Change it to meters. So that's 0.56 meters minus 0.18 meters. I can do that. Okay. So the slope right here, the slope, I'll do m for slope, right? Well, or maybe I'll just spell it out, slope, because we use m for so much in physics. I'll just see, I'll write out slope equals 3.82, and that would be square seconds per meter, right? Right, so I could maybe write an equation like this. T squared equals 3.82 square seconds per meter times L. And then if I square root both sides, kind of get T equals, and then whatever the square root of that is, square root of the answer, 1.95. And then that weird units are like seconds per square root of meters. Right? So weird units. And then times the square root of L. Okay, so something like that, right? Yeah. Okay. But the important thing is that you have the proportion correct. So you either have T squared is proportional to L, or T is proportional to the square root of L. That's really what I'm looking for here. Right. Right, that's it. Now, what's the textbook answer to this question? Like, what's the full version? Like, okay. So the full, the full version goes like this. Okay, so here's what you want to know by heart by the time you're going to the AP exam. So the time period to swing back and forth is, oh, hey, look at that. It's just like we said, it's proportional to the square root of the length. Look at that. Okay. Oh, and yeah, the gravity field does matter too. Remember, we were doing a little bit of hypothesizing yesterday. I said, what if I take this to the moon? And on the moon, it's probably really slow on the moon versus on Earth, it's regular. Maybe on Jupiter, it's like, okay. So, okay, yeah, and there's some kind of inverse type relationship there. Okay. And okay, there's also a constant thrown in the front. Right, so put it all together, looks like that. There's the textbook answer. Let's see how close is this to what we got, because we do have sort of an equation here. I got all this constant stuff come out to 1.95 in some units, right, that are base SI units. Let's do 2 pi, and then divided by the square root of, and then this could be 9.8. See, what is that? Oh, 2.00. And we got, oh wow, we pretty much nailed it. Look at that. 2.0 something and 1.95. It's like the same number, isn't it? Aha. All right, you guys nailed it. Aha. Like I said. All right, way to go. All right, very good. Very good. All right, I think we got what, 7 minutes? All right, so you guys ready to score your write-ups? All right, so I had you guys do a write-up for specifically that experiment that we just did. You guys did 3 experiments yesterday. This is the one I wanted you guys to do the write-up for. All right, you guys ready to score it? All right, so like always, I try to make the points add up to 12 points, just like AP does. So I've had a 12-point rubric here. Is this scoring rubric perfect? I don't know, maybe not, but it's probably pretty close to what AP would have. Yes, seen so many of those. Okay. So here's the question that you guys were targeting. What's the relationship between the time period and the length for a pendulum and simple harmonic motion. You guys know, of course, this quarter page was on your desk yesterday to help you guys out, right? So part one question, which AP would give you anyway, or they almost certainly give you that, right? So you guys know what you're now. But then everything else is up to you, right? If this was a free response question, sometimes AP gives you a table of data, like I was saying, or maybe a table of partial data, right? They might give you like this much, and you have to figure out yourself, well, I have to like square the time periods and show it to show that I know what's going on, right? Right. So next part, measuring equipment. See what I got here. So there were two really important tools that you mentioned. So 1 point for mentioning a meter stick or a ruler, because you have to measure the length of the string, which is your independent variable. So you have to measure that. Okay. And a stopwatch or a timer, because that was sort of your dependent variable, right? Hey, look, there's their two variables on the axis, right? We've got a x-axis, y-axis, right? Now, if you mentioned a protractor and scale, that could also be good. The scale might not be completely necessary, because if you have some known lab weights, sometimes AP will accept that. Okay, well, it's a known lab weight, it's got a number printed on it, and that's good enough, so you don't necessarily have to measure it. Okay? The protractor, maybe you can mention, because that's something you want to control. Maybe we say, I only pull back to 10 degrees, and I always keep it locked in at 10 degrees. But you guys also know, based on another experiment you did, that the angle doesn't really matter, as long as it's small. So if you do 5 or 10 degrees or 15 degrees, or if you're kind of sloppy with measuring the angle, then it shouldn't really affect it anyway, because there should be no relationship. Yeah. Okay. So definitely mention the meter stick and stopwatch. You guys got meter stick and stopwatch? All right, procedure. Now there's a lot going on with the procedure. So big picture, briefly describe the setup. What measuring tool to measure which variable. AP's always looking for these things. Okay? AP's always looking for, right? And they're going to ask you to do a lab write-up. Probably a good idea to identify what's your independent variable, dependent variable, what are you controlling, right? So that's good communication. And this is always a point, is multiple trials to reduce experimental uncertainty. You guys remember all this? Okay, so let's see what we've got here. So, 1 point for describing the setup. Here's my version. You don't have to have it word for word, obviously. Connect a lab weight with known mass to one end of a string. And the string is negligible mass. That might be a nice detail to throw in there. That's a simplifying assumption we're doing for pendulums. Connect the other end of the string to a stable stand to create a pendulum. Pull the lab weight back to 10 degrees from the vertical, or whatever angle you want. Okay? I'm just controlling the angle. And release it so that the pendulum swings back and forth in oscillating motion. Boom, there you go. That's the entire setup. That's all you do. Okay? And your description doesn't have to be word for word, but if you got it pretty close, then give yourself a point for the setup. Okay, next point. Measure the length of the pendulum from the pivot point to the center of mass of the lab weight with the meter stick. There you go. So that's how you measure the weight with the measuring tool, the meter stick. Boom, there you go. Okay, so there's 4 points down. All right, you guys good with 4 points so far? All right. These tools, go setup, measure length. Okay. All right. Next point. Measure the time for 10 oscillations with the stopwatch. And then a follow-up, so that's a point, right? Measuring time with stopwatch. Okay. And then throw in another detail here. Determine the time period for one oscillation, because that's what time period is. It's just the time for one oscillation, by dividing the time for 10 oscillations by 10. Okay. You know what I could have thrown in here? Especially if you had more time, say, okay, I think I got a little more time. I could have written in order to reduce experimental uncertainty, right? Like the error of using stopwatch. But that's the purpose of that step. Right? Okay. 1 point for multiple trials. Repeat the previous 2 steps. So measuring the length and the time, especially the time, 2 more times, and find an average time period for the given length. So these 2 steps are here. Okay, so the time for 10 oscillations, and then divide by 10. Okay. Now that, okay, I didn't mark so well on the lab table because I only got so much space on a single page of paper, and I was copying a bunch of these. Okay. But really, maybe I should have done like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, maybe I should give you guys 15 or something like that. Okay. All right. So you could do like 3, 3, 3, 3, 3. Okay. But definitely mention that in your write-up. Next up, good idea to identify the independent variable. So change the length of the pendulum. There's your independent variable. Change the length of the pendulum. and repeat this process. Do this for at least 5 different pendulum lengths, right? So if you have at least 5 points on the graph, then probably you start to make good sense of a graph. Maybe you said 6 points or 7 points, and that would be even better, right? 5 is probably a good minimum number. Okay. I did throw in a point for controls. I'm trying to get these to add up to 12. So would AP make this point? I don't know. Maybe control the mass of the pendulum bob and the initial angle throughout the experiment. It's probably good practice to specify that those are controls anyway, right? I'm not changing the mass. I'm not changing the angle or the starting angle. So I think it's up to 8 points by now. You guys good with 8 points by now? Okay.
Yeah, I have a.
All right. So next part of this process, I think we checked off all those points. Analysis. So what I write here is it's usually graphs, graph properties, or equations. Right. Now this is going to be a graph version, definitely. Right. Okay. Sometimes if you're solving for like a specific thing, like find the spring constant of the spring, that might be more of an equation type. Right? But yeah, graphs if you can make graphs. Right? And a lot of times the AP will give you actions. So what are we doing with graphs? I said maybe start out by graphing time period versus length on a set of axes. That graph would display a square root relationship. If AP prompted you to graph T versus L, then they might expect you to know that that's going to be a square root. That might be a question. Is graph T versus L, what shape does that make? You say, oh, well, that's a square root relationship. Or a sideways parabola. Should check that box. Okay. Right. Square all the time periods. Now that's where I was saying on your table, AP would, well, they would want you to come up with that yourself. AP might give you a bunch of time periods, like, oh, we got so many seconds for all these individual time periods. And they would want to, and they give you some blank columns. They would want to see, can you come up with, I'm going to square all the time periods. Or the alternative is square root of L. Did we run out of time? Great. There's the last few points. T squared versus L is linear. And so your conclusion, T squared is proportional to L. Good. All right, so square yourself out of 12. Throw that in the grade train. And I will see you guys on Monday. Have a good weekend.